Number 18, it's the trickiest one on this homework set here. Consider three charges, Q1, 6.4. You guys know what that little U thing looks like? You know what that is? That's the metric prefix for micro, okay? Which means millionths of a coulomb. Q2 is 1.3 microcoulombs, and Q3 is negative 2 microcoulombs, as shown in figure 1727. Part A, what is the electric field strength at a point 1 centimeter to the left of the middle charge? And then part B, what is the magnitude of force on a negative 2 coulomb charge placed at that point? Okay, so let's go ahead and so again, the simulations we use are very useful for visualizing. Okay, so notice we have three charges. Okay, and every charge you put out exerts a force field, right? Okay, so here's a charge, here's another charge, and here's another charge. Okay, and the tricky thing to realize is there's different amounts of forces present, charges present rather, and they're different distances. So this could be a hard problem, other than the fact that it's only one-dimensional. It's all in one line. Okay, so as long as you call going to the right positive, going to the left negative, it's not too bad. It's very doable. But I just want to help you visualize what's going on. Okay, so step one is make a little sketch. The sketch is given. I'm just going to do it right on here. Okay. Step two, let's list out all our knowns and unknowns. We're given that Q1 is positive 6.4 microcoulombs. The Greek letter mu just means 6.4 times 10 to the negative 6. It's millionths of a coulomb. Okay? So a lot of electronics, we're using small quantities of charge. So make sure you put that in your calculator properly when you solve. Q2 is 1.3 microcoulombs. So that's 1.3 times 10 to the negative 6 coulombs. And then Q3 is different because it's negative. Okay? Which means it's an attractive force is a way to picture it. Okay, so it's negative 2 times 10 to the negative 6 coulombs here. Okay, and then the question is, what's the electric field strength at a point 1 centimeter to the left of the middle charge here? We're trying to figure out what would the field look like at exactly this point right here. Okay, 1 centimeter to the left of the middle charge. So the tricky thing is each of these are a different distance from the center point here. Okay. So if this is 3 centimeters altogether, Q1 to this middle charge here, that'll just be a difference of 2 centimeters. So the distance for Q1 is 2 centimeters. Okay, I'll just call this D1 maybe. Okay, for Q2, it's just going to be 1 centimeter away. And then for the last one, if this is 2 centimeters, this is 1 centimeter, then D3 is going to be 3 centimeters altogether. Okay, and when we plug in chug, we got to change centimeters to what? To meters. Okay, actually, let's just do that really quick. So 2 centimeters. Centi means how many cents in a dollar? 100. It means 100th, right? So 1 centimeter is 0.01 meters, and then 3 centimeters is 0.03 meters. Okay. So to get the net electric field right in the middle, this is the total electric field. It's kind of like adding up forces, except we're adding up electric fields. It'll just be E1 plus E2 plus E3 is the way to think of it. Okay? And if you look in your toolbox, let's take a look at our tool. We're not trying to find electric potential. We're trying to find the strength of the electric field, which is a force per unit charge. But we're not given the force. What we are given is the amount of charge. So we're going to use KQ over the distance squared, R squared. This looks just like Coulomb's law because it's a special case of Coulomb's law, where we're not trying to find the force between two charges, but the field exerted due to one charge. So that's why it's just KQ over the distance squared. Okay? So we're going to end up using the special case form of the electric field equation, KQ over the distance squared, or the radius squared. Same. Okay? Where K is our electric field constant, 9 times 10 to the 9th. Also in our toolbox, newtons meters squared over coulomb squared. That's just the electric constant. By the way, most people in real life would never do this calculation. They'll just buy the next Kindle, iPhone, Samsung, Alias, flip phone, whatever, with electric ink, whatever. Okay? Anyways, we're almost done. Let's do it. So the net electric field will simply be equal to E1 will be equal to K times Q1, which is 6.4 times 10 to the negative 6, divided by its distance squared of 0.02 squared there. Okay? And notice Q1 is going to be pushing which way? On this center point. It's pushing to the right. Yeah? Okay? Because it's in between there. Q2 is going to be pushing to the left, so I'm going to make this a negative force right here. Okay? Minus K Q2 is 1.3 times 10 to the negative 6. Divide that by the distance squared of 0.01 squared. And then I'm going to add to that Q3. But Q3 is a negative charge, right? So it's going to actually pull it to the right. So it's going to end up being a positive number there. Tricky, right? KQ3, which is 1.3 times 10 to the negative 6 over the distance of 0.03 meters squared. Okay? So what you didn't realize is when you were playing the electric field hockey simulation, you were actually doing all this math. You just were doing it while you played the game. And if you're good at algebra, we can actually simplify this a little bit. We can just pull out the k and then just do the k at the end, right? So whatever. It's however you want to plug and chug it. So let's just get out our calculators and chug it through. I'm just going to multiply by the k at the end, okay? So you're right. Q3 is actually negative 2. I did that on purpose to see if you're paying attention. Thank you. So every once in a while, as a service to my class, I introduce errors into the teaching process to see if you're awake. I'm not awake. There we go. So it's a negative 2 charge, but because it's going to attract this point to the right, it's a positive field. Okay? So you actually have to visualize what's going on. So anyway, let's plug and chug now. Okay? So I first take 6.4 times 10 to the negative 6. I'm going to divide that sucker by 0.02 squared. I'm going to subtract from that 1.3 times 10 to the negative 6. Oops. There we go. Second EE. There we go. Negative 6. Divided by 0.01 squared. I'm going to add to that 2 times 10 to the negative 6. There we go. Divided by 0.03 squared. And actually on these tricky ones where there's a lot of math, I usually give you guys a bunch of chances, like 5 chances or something, okay? In case of brain fart calculator errors here, okay? Divided by 0.03 squared. Bingo. And we get that. And then I didn't multiply that by k yet, which is 9 times 10 to the 9th, okay? Newton meter squared over Coulomb squared. That's the electric field constant. And we get a net electric field of 4.7 times 10 to the 7th. And since it's a positive value, it's going which way? To the right, okay? And the units are newtons per coulomb, okay? Why did I not make the second charge negative? Good question, because if I zoom in on the diagram here, let me zoom in a little bit here. Okay? This is the point I'm looking at right here. It's getting pushed to the right by Q1. It's getting pushed to the left by Q2. And then Q3 is sucking it to the right. Okay? So that's why it's positive, negative, positive. Okay? And the final direction will be along the positive x-axis. Okay? Now the final question is, what is the magnitude, let me just finish here, of the force on a negative 2 Coulomb charge. Okay? So now it's pretty easy because E equals F divided by Q. Therefore, if we want to just use our force equation, force is just equal to Q times the electric field. Okay? Right here. F equals Q times E, or E equals F over Q. So once you know the strength of the electric field, then we could find F by multiplying Q times the electric field strength. Coulombs times newtons per coulombs. So all this is it's 2 times 10 to the negative 6 multiplied by what we just got, 4.7 times 10 to the 7th. Okay? So if we just take out our calculators and plug and chug, multiply that by 2 times 10 to the negative 6. We don't have to worry about positive or negatives. It's just asking for the magnitude. Okay? We get a final force of 9.4 times 10 to the 1st newtons, which is just 94. Okay? And technically, a negative charge would, let's see, end up moving to the left because it's in the opposite direction of the field. 9.4 times 10 to the 1st. So not a hard problem. You just have to visualize what's going on.